Did you know that chemistry exists in everything? It exists in the air we breathe. It exists in the ground with the advent of rocks. And it exists in pharmaceuticals. And it gives us tren. Anything is possible.
Nill by the chemistry guy.
Oh.
Nill by the chemistry dad.
More.
Nill by the chemistry guy.
Stoichiometry rules.
Nill by the chemistry guy. EV equals nRT.
Atoms
are
are
very
small.
Atoms.
Nill by the chemistry guy.
If you want to truly understand chemistry, take my manners and speech patterns and never replicate them. And I'm speaking about this from experience. But if you want to truly understand science chemistry, you'll need to know this. Chemistry is the composition of matter and the changes it undergoes. It exists everywhere. There's so many types. Organic chemistry, physical chemistry, or analytical chemistry. It's so vast. And you know how you can help us out? We've spent a lot of time shrinking this vast subject into 7 minutes. So smash that like button. But how can we use this data without a way to analyze and classify it? That's why we have measurements. And we'll be heading over to our measurements expert, Clyde the chemistry child.
In chemistry, we use the metric system to measure everything that we do in chemistry. This includes seconds for time, we have grams for like the mass, and we have Kelvin for heat. And to get to Kelvin from any other unit of measurement, especially Celsius, you add 273. So you take the Celsius, add 273, and that gives you Kelvin. And because of this, we have different prefixes for each of these units, which starts with nano, micro, milli, centi, deci, which are the before, which are less than the regular prefix, such as grams or meters. And then we have deca, hecto, kilo, and mega. And by the way, each of these prefixes is 10 times the last, which makes this whole metric system so easy to understand. The metric system can be used to help us find percent error, which is the error of a certain calculation. And with that certain calculation involves 3 states of matter: solids, liquids, and gases. We can quantify or categorize these 3 states of matter as not as solids, as compounds, mixtures, and elements. And with those, there are 2 different types. There are physical and chemical changes that can be done to each of these 3 states of matter.
Wow. The atom is really small, and it contains protons, neutrons, and electrons. These atoms can combine into elements such as iron and helium, and each of these elements can be distinguished into isotopes, whereas the only difference is the number of neutrons.
The periodic table is huge, and we can find all these elements by using the categories 1, 2, 3, and 4, which correspond with the letters
S, P, D, F.
As well as this, the periodic table has 3 main classifications: metals, metalloids, and non-metals. And each of these classifications has their own distinct trait, like the metals' shine and luster, and their hard out exterior. While metalloids have properties of both metals and non-metals.
Get back to talking about compounds. There are 2 types of compounds, ionic and covalent, and we can make sense of these using the Lewis dot structures, which show the valence shell. And this valence shell follows the octet rule, meaning that there are 8 electrons in the valence shell. And the octet rule means that each electron needs to, in a chemical equation, needs to have the octet rule fulfilled, meaning each chemical or element will have all of the 8 electrons.
Whoa! Let's get back to talking about covalent bonds. They have 2 different types, polar and non-polar, where like dissolves like. These also have their own shapes, called straight, bent, pyramidal, tetrahedral, and trigonal planar. These are all held together by intermolecular forces, which are forces that hold atoms together, which are usually weaker than intramolecular forces, which are the forces holding atoms together on the inside. There are also chemical equations, which are also known as chemical reactions. And these have a couple different parts. They have single replacement, double replacement, synthesis, decomposition, and combustion.
Oh hey, didn't see there. The name's Nill, but you probably already know that from the beginning of the video, but let's just keep moving on. In my opinion, the best player in the world in basketball is LeBron James. His scoring record is so great. But you know what's even bigger than this scoring record? Avogadro's number. 6.02 times 10 to the 23rd. The significance of this number is that it's the amount of particles in the chemistry mole. The mole is really important in chemistry because it's like the point guard, it's the facilitator, it's the Kobe to your very own Shaq, it's the Magic to your very own Kareem. It basically handles the conversions between moles and liters, moles and grams, and moles and particles. Let's just say we're in the Game 7 finals, I'm the point guard and I'm passing it to LeBron. LeBron's the mass, and I would have to multiply the number of moles, me, times the molar mass of LeBron's element. Just like here.
I believe I can fly. I believe I can touch the...
Next, I'll throw a chest pass to Kyrie, the particles. Now, to do this, I'd have to multiply me, the moles, by 6.02 times 10 to the 23rd. Atoms, moles. The last meaningful conversion we have to do is between moles and liters. Now at STP, this is pretty simple. We just have to multiply the amount of moles times 22.4 liters. But when not at STP, we have to use the ideal gas law, which is basically PV equals nRT, pressure in ATM times volume equals temperature times moles times the gas constant of the specific thing you're using. And we might be wondering, what's ATM? I just said pressure in ATM. Well, ATM is a unit for pressure, and a way we can transfer this between other ones is 1 ATM equals 1 millimeters per mercury. 1 ATM equals 760 millimeters per mercury equals 101.3 kilopascals. Now, to end this, I'm going to end up passing the ball to my very own Clyde, this chemistry child. All these conversions add to stoichiometry, which is when we use these moles and these conversions to create equations to transfer between the different units. For example, a common stoichiometry question would be how many particles are in 20 grams of iron? In this equation, we would have to transfer from 20 grams of iron to moles, and then after that, we'd transfer from moles to particles. Alright. Now that we just finished up with the basic stoichiometry, let's get in deeper into gas stoichiometry and the laws that come with it. First, let's talk about Boyle's law, which is the relationship between pressure and volume, which are inversely related. Basically, as pressure goes up, volume decreases, and vice versa. In contrast to this, we have the relationship between pressure and temperature, where as pressure goes up, temperature goes up. Finally, let's talk about partial pressure, where the pressure of all the smaller gases add up to make the pressure of the final gases. Another important part of stoichiometry is solution stoichiometry, and a crucial building block of solution stoichiometry is the concept of homogeneous and heterogeneous mixtures. So basically, these mixtures have a concentration of a substance, and this concentration can be used to calculate other concentrations by using the molarity, the number of moles over the volume of the substance.
Although my jumper is heat, there are other ways to measure heat in chemistry. This is called thermochemistry. You can use Q equals M times C times delta T to measure the heat energy in calculations. This is done in kilojoules, and because of this, there are two different types of thermochemical equations, endothermic and exothermic. One gains energy and one loses energy.
Calculating the rate of a reaction is used to see how fast your reaction will happen, and we can do this with the average rate equation, which is the average rate equals the negative change in concentration over the change in time. As well as this, we also know that for a reaction to happen, we need to reach the activation energy, which can be lowered by using catalysts. One specific type of reaction is a dynamic equilibrium reaction, which shifts left or right based on the changes in concentration, total pressure, total volume, and temperature. Acids and bases are managed on the pH scale, with 1 being the most acidic and 14 being the most basic. Now, if I step on the scale, the more weight I am, the more basic I'll be. The less weight I am, the more acidic I'll be. And you can see the pH model right here. Next, there's also other ways to measure if there's acidic or basic. This is the Lewis, the Brenston-Lowry model, and the Arrhenius model. In addition to this, buffer models are also used to resist the change in pH.
Psych!
Wanna make a move to chemistry land. Go up to class on time to learn some stoichiometry. And I use molarity diagram plus PV equals nRT. 4.02 times 10 to the 23rd is Avogadro's number.